recording. Okay, so let's talk about how we're gonna deal with ray optics. Okay, the first thing we're gonna try to clearly define is what an object is. Okay, right? If you see an object in front of you, you know what an object is, but maybe we have to gonna do some easier definition to model these objects so that we can do these things called ray tracing. Okay. So imagine you have a Christmas tree in front of you, right? Or just any tree, it doesn't have to be a Christmas tree, right? What we actually care about, right, is basically kind of not the detail about the tree itself. We care about where the light is coming from on top of the tree compared to where the light is coming from on the bottom of the tree. Okay? The reason we care about that is that that's actually the length of the tree, right? How tall this tree is. Okay? I mean, in order for us to see the leaves and the ornaments and stuff like that, you probably need better vision than that. But for now, what we're going to do is we're going to try to treat this tree as just, okay, we're trying to figure out the length of this tree. Okay? And so therefore, the light that we see from the top of the tree and the bottom of the trees are the most important ones, right? Okay? Okay? So this is an object, okay? So whenever we see an object that has a certain height, we're going to, put it vertically. And then we're going to have rays that's coming out of the top and the bottom of the trees, okay? And this is where, so if you see the top of my head, I have rays coming out of the top of my head. That's why you can see the top of my head, right? And then if you see my shoes, right, maybe the red part of my shoes, there's rays coming out. And that's the beams of light that's coming from my shoes and hitting your head, right? And that's why you can see it, okay? There are also a couple of other side definition, okay? Right, so you can see that these are considered point sources where, even though the book didn't draw it, I mean, all these rays actually technically goes in every direction, right? Typically, we care about the ones that goes to the right because we're going to place the object on the left, and then we're going to see how these rays actually progresses forward. Okay, so for point sources, it's just a dot, right, that beams light in every direction. What happens in a lot of cases is that, let's say you have a bunch of objects, like a bunch of, let's say you have a forest instead, right? And all these trees are kind of like, beaming light in every direction, but the part you actually care about is the one that's going to be arriving at your eyeball. I'm going to try to draw an eyeball here. Wait, that's a really creepy eyeball. How do you draw an eyeball? Sorry. All right, that's my best version of an eyeball. Okay, all right, okay. All these beams are actually kind of arriving towards your eye, parallel to each other. It's an approximation, but we're going to use also this approximation in order for us to do some ray tracing also. Okay, and these are known as parallel bundles. Basically, they're all the beams are parallel to each other, right? This is if you have a source that's far away. Okay. Multiple sources far away. Okay. Okay. Away. Okay. If you have a single source that's close to you, you have to use this little point source thing. Okay. And so before we move on, what we need to do is also define this thing called an aperture. Okay. And this is where a little video will be helpful. Okay. An aperture is basically an opening where the light passes through and then and goes through the other side. Your own eyes is actually an aperture, so the little hole, the iris in your eye, right, is that where light is allowed to go through, right? The light is coming out from here into the back of your eye, and actually I have a picture of that. Actually, I can show that to you right now. Okay, right. What happened is that the light goes in. I mean, this is not to scale, right? And what happened is that as the light enter in your eye, it goes through your iris and through your lens, and it actually hits the back of your eye, right, where it actually forms an image. These are where the optical nerves are, okay? The image that you form is actually upside down in the back of your eye, okay? And your brain flips it back right side up. There's actually an experiment where they basically put a camera in front of a person with a screen, and that camera always flips the image. So after walking around with that upside down image in front of their eye for about a week, the person's brain actually flipped it. Okay, it actually flipped it back right side up. Well, it did it upside down, and then upside down. So I guess that's right side up. Anyway, it makes sense, right? Where it's actually your brain that's actually flipping the image back right side up. And you can actually, with about a week of training, you can actually do this if you wanted to do that to yourself. Anyway, but the point is that when an image forms through a little slit, right, in chapter 33, these are called slits. But now we're going to call them an aperture because we don't care about, the wave, basically the wave nature of light. We just care about this beam of light going straight through and going again to the other side, and this beam of light from the shoe of the tree going straight through and getting to the other side. So the image that's formed is actually upside down. Okay, I'm going to show this little video just to prove that, and you can do this at home if you want. And the volume is go up. Of course it's not.
How to transform a room into a camera obscura. A camera obscura, also known as a pinhole camera, is the concept that made modern-day photography possible. Now use the same principle to turn a whole room into a walk-in camera. You will need a room with one window, 3 or more 28 by 22 inch sheets of black poster board, a flashlight, a utility knife, and duct tape. Optional, a white sheet, a blanket.
Basically what you do, I can fast forward. Okay.
Step 6. You should now see an upside-down image of the outside world.
So what they did is basically they cover all the windows, and then with one window they just have one hole that's bigger than a millimeter in diameter, right? So basically I think they use a soda bottle or something like that. And then as the image comes through from the outside, it gets flipped upside down, just like it does in the back of your eye, right? And that's why they're seeing.
Projected onto the wall. Why? Since light rays travel in a straight line, they hit the objects outside, pass through the small opening of the lens, and transmit an upside-down image of the objects on the opposite wall. This is the same method cameras use to capture images. Step 7. Unless you want to cover your entire...
I need to do step 7. Okay, does that make sense? Where whenever an image goes through a small opening, right, it turns the image upside down. Okay, and that's because, right, the ray that comes from the top actually lands on the bottom and the back of the box, right? And that's basically how a camera works. Okay, a few more definitions, right? So we're going to call this going to be H naught, right? So actually not, I shouldn't call it naught. The O here stands for object, the height of the object, okay? And this O here also stands for the distance to the object, okay? And then the I here stands for the distance to the image, okay? And this is the height of the image. The I stands for image, and the O stands for the object, okay? So what we can do is actually start doing some, similar triangles here and just do some analysis real quick, right? Because we can probably relate HI to HO, right? The height of the object to the height of the image, right? So if I just draw some triangles here, what happened is that, well, this triangle, oops, this triangle, just do that with the highlighter, okay? Right, this triangle, right? Can't do that, right? And then the purple triangle in here, purple, come on, purple pen, right? Right, the red triangle and the purple pen triangles they're actually what's known as similar triangles, right? Because the angle of opening here is the same, right? These angles are exactly the same as each other. It's just the lengths of the triangle is different, right? Okay, it's basically kind of like a zoom in, zoom out version of it. So therefore, what we can say is that, well, whatever the length of D is and the length of H is, they should be related to each other, right? So therefore, H naught over D naught, right, is going to be the same thing as HI over DI, right? Okay, and if you solve this equation, right, so HO over, actually I want to solve this for HI. So I solve this equation for HI, right, HI over HO equal to DO. Did I do that right? Yeah. All right, sorry. I need to do this in 2 steps. Okay, I want to solve this equation for HI, so I multiply both sides by DI, right? And then I'm going to divide both sides by HO, because I want that ratio. Okay, these cancel out. These cancel out. So HI over HO is actually going to be DI over DO. Okay, right. So actually, if we know the distance from basically the camera to the object, and basically the lens length inside the camera, right? We have that ratio. You can actually predict how big the image inside that camera is going to be. Okay, we're talking about this in terms of camera, but this works for anything that has basically an aperture in front of it, right? We already kind of talked about how the brain does this, right? So for example, this distance, how many of you guys know how big your eyeballs are? It's about an inch in diameter. So this distance here is actually about 2.5 centimeters. Okay, so that's basically what your DI is going to be. So the size of your image is going to be scaled down by however far. Let's say this tree is 1 meter, 10 meters away. Let's just do 1 meter to make easy math, right? Right. In other words, 100 centimeters. So the image size is going to get reduced by a factor of 40, right? Because 100 divided by 2.5 is a factor of 40, right? So in this case, HI over HO is going to be 1 over 40th, okay? Right. There's a neat thing, so we don't have that much time, but let's do this exercise today, okay? You might be wondering, right? So the image forms here, and does anyone know what this is? The optical bundle is actually called the vertebrosula ezamia, whatever it's called. Actually, that's the disease. I forgot about that. Okay, this is actually a bunch of optical nerves that actually creates what's known as the physiological blind spot, and you can actually test that you have this. And how many of you guys done this before? Yeah, one of you. So you may have to stand up. So what you do is, if you cover your right eye, you want to look at the right dot, and then as you go closer and closer to it, basically the plus sign, what happens to me is right here, disappears, and you only see a plane of green. Okay, the same thing happened, right? If you cover your left eye and only look at the cross, as you walk towards it, the angle it comes in at, right, at this one spot, basically the black dot on the right disappears. And what happened is that your brain basically covers that up by just assuming it's the same color all over. Okay, and that's a sort of an interesting thing. Okay, and if you're interested in doing that test yourself, we can do that right after class. But the idea here is that all of these images that forms on the screen, right, they can be traced back to a source. So let's say you cut out a little L shape in a card, right, and you have a point source here, okay? What will happen is that the light basically will form an image of an L on the other side, right? So hopefully that makes sense. So I'm going to give you guys a harder question before we wrap up today. So let's say we have a source of light that is horizontal, let's say kind of like a fluorescent tube, right? And we place it in front of a vertical aperture, okay? What type of image will form on the other side, okay? What shape would it be? Would it be also just a vertical bar, just like this shape? Or would it be a horizontal bar, like the light source? Would it be a box? Or will we get an interference pattern, okay? And this is assuming that the width of this is bigger than a millimeter, okay? How many of you guys think is A is going to get a vertical bar, right? The same shape as the cutout. How many of you think it's going to be horizontal, the same shape as the light? A couple of you, okay? How many of you think it's going to be C? It's going to be a box. Okay, a few more of you. And it's not going to be the interference because I just stated that we don't need to worry about the interference pattern, right? So let's do some light tracing here, right? So the way we do this is that we just make a big screen in the back, right? Let's say the light is red. So what I'm going to do, I'm going to take the left-hand point of this light and basically trace the light as it goes through the top of this and where it ends up on the screen. I'm going to also trace this light, right? It goes through the bottom of this, it ends up on this screen, right? right? So because all these light sources, we should assume it's just going to be like in every direction, right? But these are the two rays that are interesting to us, okay? I'm going to do the same thing here on the left-hand side. What's going to happen is that I'm going to trace it until it hits the green screen here, right? I'm going to trace it through here until it hits the screen down here, right? So it actually kind of forms an image of a box when you do that, okay? So those of you who thought it was C is correct. Okay, so that's all we have time to cover today. So any questions before we wrap up and talk about the midterm and the final? Okay, so I'm going to stop recording.